Okay, let's assume we have a quorum. I had a good question at the end of the lecture last week, and it made me realise that I had made some assumptions about what stateful and stateless mean, which were probably known to me but not known to you. So, any running program contains state. So all programs are by definition stateful in the sense that while they're running, they contain state. The definition of stateful and stateless says whether they have state when they are not running. So program's there, it gets a request in, it does something. While it's doing that operation, it has state. The question is, does it maintain that state when it's not actually performing the operation or not? So a stateful application is an ordinary one, and request comes in, and your request comes into your copy of the application because it's got your state inside it, got your session state whatever inside it, and it knows what you're up to because it's got local variables saying what you're up to. Your session state is there. So it does your operation, it sends back the response to your request and keeps all that state. So you are tied, that particular program instance is tied to your client because you talk backwards and forwards to each other. So that's a stateful program. That piece of code holds those state variables between requests. And there's a one-to-one association between that particular client and that particular program instance. A stateless program gets a request in, restores the state appropriate for that client, performs the operation, saves the state somewhere safe, and then throws it away. It saves it somewhere. So in between the operations, it is not maintaining any state for that client. Which means, of course, it can be shared. So the next request comes in from another client, it can come to the same application instance, which goes and recovers the state for that particular client and does the operation, puts it back into the state store again and returns the result back. So it's stateless in that in between operations, it does not contain any state. So now we can share them across clients. So here we see we've got a little pool, we've got 5 clients, we've got 3 of these application instances, and the state goes backwards and forwards to some type of state store between operations. So what we probably have is some type of magic key coming from the client, and the key gets picked up by the application. You say, oh, this is state 500, this is session 581, I'll go and retrieve 581's session state from the state store. Whoop, now I can do the operation for you. And that's the way you'd normally write this type of code. So stateful and stateless. Of course, programs always have state, just whether they have any between the operations is the question. Does that make more sense than what I said last week?
Yes, the client have to have some sort of like maybe the browser has that.
Yeah, so what you typically will do, if you notice all the pigeon droppings you get in a typical URL, and then some 80-digit hex number, that is going to be used by the server side to say, that's who you are. Thank you for telling me. So that type of, there's some state being passed backwards and forwards in those pigeon droppings, but amongst that will be some magic key that the server side can use.
So if a man in the middle sort of an attack, if you were able to extract this session ID,
you possibly could, but there might be some other checks on it as well, like it might be a single-use token. So the next time you use it, that token's already been used, so you could do that. And that's one of the things that cookies are used for as well. So you might put something in a cookie saying, next time you're asking me to do something, tell me who you are by looking in your cookie that you've got. So I'm passing it from the client to the server, and then the client will just keep track of it. Okay, so for those who just came in, I just did a refresh on stateful and stateless. Was it your question end of last week? Yeah, so it's got to do with the state when the program is not running an operation. So when it's between operations, whether it is keeping state or not. So I will try to refresh the slides online with this extra slide, but okay. This week's complicated presentation. Oh, I'm sorry, wrong button. One too low. There we go. Distributed computing. So we're moving our way sort of down the complexity path, and when you start looking at the code that is used in the lab examples to implement this stuff, you look, oh, this is so complex. Well, yes, it is. A lot of that complexity is either generated for you or it's there because people want options. Oh, I want to be able to use this. Okay, fine. We've got some way of doing it. So there's a lot of inherent complexity there because people want lots of flexibility at the same time as you want simplicity. And you can't have both. So what you might find is a lot of generated code, boilerplate stuff, which does things. So you haven't got to write it, but you can go and change that a little bit there. You change an option in the config file and the behaviour will change. But when you're diving and looking at it and think, oh, this is just horribly complex, there's layer after layer and complicated frameworks. Yes, they are all like that. But let's talk about distributed computing. We don't want that one. Distributed computing, the opposite, well, let's look at the opposite of it, which is centralised computing. You go back once upon a time and you had a big honking, expensive mainframe computer somewhere and everything ran off terminals going to that. That was the extreme. And then people started saying, oh, you know, computers are actually getting smaller and cheaper. Why don't we distribute them? Why don't we have local computing so that every branch can have its own computing? And if that branch's computer is down, the others are still working. So we've got a lot of autonomy, independence, flexibility. So that was the goal, that you stop having this dependency on a single point of failure and instead push the computing out. And as soon as computers became cheap enough to do that, this was a goal. And then you want to be able to transparently integrate all those bits of the company. You want warehouses to be able to talk to each other. And oh yes, I haven't got it, but the warehouse in Melbourne's got a copy, and we'll get that sent up to. So you want to be able to, for all the bits of your distributed system, be able to talk to each other. So you want to be able to make requests of bits of code that are running somewhere else in our system. We want to be able to access data living somewhere else in the system. We want to be able to take computational load and spread it out. The distributed might be amongst multiple machines sitting in the same room. We're using that for scale out load balancing. And we want to be able to take a gun and shoot one of the computers and it says, oh, just a flesh wound, and one of the others takes over its load. We don't quite shoot them, but it's very popular to demonstrate by pulling out the power cable from something. Well, seems to have had an accident. Does it survive? So it's been a long cherished ideal. People have been trying to do this in various guises for most of the history of computing, from the 70s and 80s basically, and it's obviously really difficult, but people do it because you have no choice. There's an example of one of these types of systems. We've got N warehouses. They all have their own local computing. They're all running the same software. They're all looking after their own stock. They all do their own deliveries. And we have two bookshops talking to them. They're both running their own systems. And obviously, they're all talking to each other. So, is that in Ian's book, that diagram? It might be. It's familiar. I don't know whether it's one of the ones I did for Ian's book or not. But That's just a simple little distributed system. Well, there's lots and lots of questions there. If I go back a page, we've got all those lines in the middle here. And the question is, what are all those lines? When this piece of code here wants to see whether that book is in stock at warehouse 2, how does it do it? How does it make that request across a network? How do we get requests going from the client to the server and back again? What type of protocols do we have? We're going to have some type of request response protocol there, and there will be many of those. We may have many of them in the same system, both for historical reasons and because different types of those protocols will have strengths and weaknesses, and some will be more useful for some applications than others. So if I'm doing stuff within the same box, then I might make do with a very lightweight and very fast protocol, because I'm not worried about some of the problems that occur when I'm going across a geographically large distance. Or if I'm going if I'm crossing a trust domain boundary. If I'm all inside the same box, then all the code running on here is my code, therefore I trust it. And I know that all the users have been authenticated, otherwise they wouldn't be on my system. That's not true when I'm going across to somebody else's system, which may not even be in our own organisation. So depending on the boundaries, the trust boundaries, the performance requirements, different choices for those protocols may be the appropriate ones. And you may be using lots of them. So the protocols that we talked about in the very first lecture are made up of messages, the allowable orderings of those messages, and the expectations. Designing protocols is not easy. Designing good protocols is not easy. You might run these protocols directly on top of a network layer in TCP, UDP. People do that, and historically that's the way people do it. If you have a protocol like SMTP, the mail protocol, it runs directly on TCP. So someone said, okay, I've got a mail client and a mail server. Let's define a series of messages where I can send email, receive email, etc. And I'm doing that as a series of messages that are plumbed straight on top of the TCP layer. A lot of file servers will have a particular file service protocol, SMB, which will be running on some quite low networking layer. They're doing that either for historic reasons, because there was no other layer for them to build on, or they're doing it because that's going to give them the highest level of performance. Doing this type of thing on the bare wire network layer is technically challenging and difficult. The protocol design's hard. You really should have correctness proofs. You don't have holes in the protocol. Get to a spot where you think, I don't know what to do next. Yeah, it's not hard, not easy. Certainly not something you want an average programmer to do. And an average programmer sounds like I'm being disparaging. Now, the average programmer is the average programmer. There's that saying that George W. Bush didn't believe that half the Americans were below average intelligence, which says something about George Bush. But an average programmer is average programmer. It doesn't mean poor programmer, it just means average. That's fine. So you really don't want the average programmer to see all those challenges and all that complexity. So the goal was, we'll just make it all go away. We'll make distributed computing just look like local computing. You've got a programming model you're used to. We'll just magically put a bit of network in between. So if you're used to writing procedural code with procedures in it, hey, you keep on calling procedures. That's cool. And somewhere between you calling that procedure and something actually running your request is a network. But you don't see it. You call procedure X and it magically runs. But what's sitting on top of, we'll talk about later, is a whole pile of networky stuff, which is getting your message across to a remote server where your remote code can execute and give you the response. So, procedure calls. There's been a swag of those. Then object-oriented programming got popular, so we had remote objects, and then the shortcomings with that were seen, so we started having remote components, and it's been a series of these things where we've just gone from one programming model to another programming model to another one, but the whole idea is that distributed computing is hard, so we'll hide it from you. You think you're doing something local instead. So you don't need to worry about writing a protocol and designing and proving it's complete. You just go and call a method or create a remote object and call its methods, however you do it. You could, if you wanted to, go and build explicit messages, and there are good higher level message passing protocols around there which are extremely useful. We'll talk about those later as well. And now there's the whole services world where I'm using web services type technologies as a networking layer, and I'm doing, here, have a request, get a response back, but I'm using a web type layer on top of HTTP, on top of etc., etc. So we've got another higher layer there. But although this is a lovely thing to do, let's hide the complexity, the unfortunate truth is that distributed computing is nasty. And although we can hide the complexity, it really is inherently very different to local computing. I'll do the bit on the bottom first. The nice thing about distributed computing, it has lots of interesting new ways you can fail. If I call a local method, then how can it fail? You know, the machine's either dead, in which case I didn't make the call because I'm on the same machine. If I'm calling one of my local objects, I call it and it happens, right?
Why is the procedure calls went away and now the messages like REST and all is there?
So why is that?
Why is the COBA and RMI and all that is no longer? I mean, it's there, but it's still.
They all still exist.
We go with the REST and all that. Is it just because this 480 being more stable than?
I'll cover some of those a little bit later, and then I'll have a bit more background on it. There's a slide on history later, and some of it is fashion. You can't cope. You can't lose. You can't fight a fight against fashion. Okay. So, distributed computing. The problem is that it offers you lots of interesting new ways that you can fail that you can't fail with local computing, but it looks like local computing. You can have partial failures. There's latency issues. I'll talk about some of these problems. And there's a guy, this is quite old, this list from Peter Deutsch, it's probably from the 80s. So at that stage, he thought it was worth writing down these lessons that people who've been doing distributed computing had, these are rules, it looks like it's simple, but it's not. So the fallacies, the network is reliable. So you send off a request, it never gets lost. No, you can lose messages. You can lose responses. Losing responses in some ways is nastier than losing requests. Latency is zero. When you ask for a request to go across a network, it's always infinitely fast. Unfortunately, it takes time. There is real and significant latency. And your programming models may assume that you don't have latency. Bandwidth is obviously not infinite. The network is not secure. You have to worry about security. The topology doesn't change. Someone doesn't plug something and unplug it and move it somewhere else. The way you used to send that request is now different. It's got to be routed across to somewhere else. There's only one administrator, which means that that's a fallacy because now I have different administrative domains. I can't just go and get that done. I've now got to negotiate with someone else, or someone else might have decided to reconfigure something for their own purposes. There can be interesting problems to do with administration. So those 8 fallacies, which was written down probably in the 80s, perhaps 90s, are as true today as they were then. But people say, distributed computing, we'll make it look like local computing. Yes, except for these interesting little problems. We're going to look at what it means to do a remote method call, and when I say method call, it means procedure, etc. They're all basically the same. I assume you all know how we do a local method call. You've all done hardware courses, you've all looked at instruction sets, you've all done assembly programming. If not, you should have. So we've got our machine has some type of call instruction. It might be called call, and that's effectively a branch to some other piece of code. So we're running along, we do a call, we've got a current location, and we're going to jump to somewhere else and start running code over there, and the call instruction simply says, go and do the jump, but remember where we are just now. It may also do some saving of states and things for us, but that's not essential. And we'll have some agreed way of passing arguments to the piece of code we're jumping to. We might put them on a stack or pass them in registers, and then we run this remote code, and when we're finished, we use another special hardware instruction which says return, and that takes that saved return address and jumps back to there. So that's how ordinary method call returns work. And different languages have different runtime conventions for the way we pass the arguments, etc. And if we've got an OO language, we've also got the complexity of finding the object for calling and then finding the method entry point inside the object. So there's some dispatching complexity there. But that's all pretty straightforward. When we put a piece of wire in between the client and the server code, we're going to do it by introducing a piece of code here, which you can call a stub or a proxy. And just to make life easier, this is called a proxy or a stub. Don't worry, two different communities just call them overlapping things. But these slides are written with stub and skeleton, it doesn't worry me. They're both stubs. So what we do is we generate on your behalf a little piece of code that this calls. So it wants to do a method call. Instead of actually calling the server code, it calls this physical piece of local code. And this physical piece of local code knows about the network. So this is the proxy for that on the client side. It's a proxy for it, and so we do a call on this piece of code. The magic word is marshals. That's the jargon word. So we take the parameters and some other things, and we put them into a message, into a request format, and then we know how to send it across the network, and that's the calling side. So we take our method call, we physically call this turns the method call into a message and passes it across the network. That's all cool. That message arrives here on the server side, and it does the opposite. It's listening on the endpoint for that service, it gets the message, it unmarshals the request, extracts all the arguments, constructs a stack frame, and calls the piece of server code. And that question we had at the beginning about stateful and stateless, of course, that involves when I'm doing this call from here to here, whether I'm going to an instance of this piece of server code per stateful thing, or whether this is just a piece of code that I create on the spot. If you're doing OO programming, it's sort of stateless OO programming is sort of an oxymoron, because objects are by definition are things with state in them. So a stateless object is one where it sort of dehydrates itself and vanishes and then rehydrates itself and comes back to life again when the next request comes in. So stateless object programming is a bit odd, but you can do it. So then once it's done the marshalling, it just does a call, bloom, and then on the way back, we just go the opposite way. So this calls back into the skeleton, which marshals, passes it across, it arrives back at the stub, which unmarshals, and does a return back to the client. So that's basically how they all work. So we've got messages, we've got method calls being turned into messages, and responses being turned into messages, and that's it. So that's the type of stuff we'd have in a request and a response. I don't know where I stole this from. I think this might be a Microsoft one from the object endpoint ID, but the requests physically in this system look like this is what a request has inside it. The message has a, what am I calling? Which interface in that object am I calling into? What's the name of the method? Or how to get it to the method? Other bits of headers that might be relevant, and my parameters, the in parameters and in out parameters, the parameters I want to pass across to the server code. And the response is a status code. Did it work or did we fail miserably? Any extension stuff, and the results, the out parameters and in out parameters coming back. And that's exactly what my messages look like. Getting a bit more real. This is the bit in the middle, is that same diagram from the previous slide, and this is the Corba, also used by Java, physical message which implements that, IOP, and this is a Microsoft one that implements the same thing called DCOM, and you can see that's what they contain. We've got a message size, protocol extensions, so they all map onto those things. So real messages involved in this stub proxy thing skeleton are just messages like that. Theoretically, you could look at them. So if they look like that, and just to be even more horrific, they might look like that. So these things used to be binary, and then someone invented XML, and then XML begat SOAP, which is an XML-based version of that previous slide. So here is a request, a SOAP request in XML. Anyone know what the actual parameter being passed? So 2 questions. What's the method I'm calling, and what's the parameter being passed to it? Get last trade price is the method name, and the parameter is a symbol called DIS. Yeah. The rest of it's just boilerplate. But well, that's XML for you. We've got a paper that I did with a student where we're looking at the performance of this type of stuff. For his PhD, he did an alternative encoding, but the interesting work was doing performance studies of this. And it turns out that although it's verbose, it doesn't really matter very much. I don't think I didn't include that slide. We did some performance studies. We had a fast wide area network to Canberra, gigabit unloaded wide area network. We had fibre down there, and so we're just doing tests, and you can get there's about 10 milliseconds return trip to Canberra for this type of stuff. So that was fine. I'll talk about latency next, I think. Okay. And I'll talk about latency, and I'll come back to those numbers. So we had those stubs and skeletons. The question is, where do they come from? They're pieces of code, and you don't want to be writing them. And the answer is you don't. But at the same time, you want them to be highly specific to their task. You don't want interpretive code where it says, oh, what's this method look like again? Oh, I better go and... No, these are bits of generated code, and they're generated by your remoting system. So your compilers or development environment, whatever, will go and generate those things specific to a particular remote object. So you might say, there's a remote system over there and it's got these services available. I want to go and call it, and you point development environment at it and say, go and generate the stuff I need to talk to that, and it will do that. Or I might have an abstract description of a remote service in some language, and there'll be a compiler that'll take that abstract description and generate that code for me. And So they just need to know what the code they're calling looks like, what its interfaces are, and the calling conventions, how to actually physically do things, how to do the network, what the runtime conventions are for the programming languages involved. And we'll generate these magically. I said you might be an abstract language. There are things called IDLs, IDLs, interface description languages. And there's one called WSDL, which is the Web Services Description Language, and there's a number of these floating around. These are abstract definitions of services, of interfaces. And then there are tools that will take one of these descriptions and generate all that code for you. It says, oh, I've got a method, I've got these parameters, etc. There you go, there's the code for you. Now that might be hidden by your development environment, but you might also have to go and have a tool that will go and do that in some way. And once you've got this generated code, then you install it somehow. It'll probably be taken care of you by your framework. There has been pushes at times to be able to have these types of things in repositories, so you can go and do a search and find them. And yes, you probably will have one of those type of things around, but the one repository to rule them all has manifestly failed many times, but there are smaller repositories around. Ah, good. There we go. Now I can talk about your question. So this stuff all started off with when procedural languages were popular, and obviously what you wanted was remote procedure calls, and so they're the oldest of these technologies, and they're still widely used everywhere. A lot of the underlying plumbing in operating systems is this stuff. If you've got a distributed function operating system, it's probably running on an RPC protocol. One called DCE, where did DCE come from? From the Unix world, I think, and that's been propagated around. So lots of it's still being used. And then the OO fashion came in, and everyone wanted to be OO pure, and procedure calls weren't good enough anymore. We had to have objects, and we had objects. So Corba came in, a set of standards from a group called the Object Management Group from OMG, and that lets you go and do remote objects, genuine objects, and you go and create an object on a remote machine. And it's a stateful object that'll sit there, and I can call it, and there's all the infrastructure you need to go with that in order to directories to find objects, etc. It was very complex, and the very first version of the predecessor to this course, Ian and I had two courses, design of distributed object systems and programming distributed object systems. And at the very beginning, we spent a considerable time talking about Corba, because it was the hot technology topic of the day. A couple of years later, no one wanted to know about it. But what killed it was its inherent complexity, the fact that remote objects are not a really good model, and the adoption of components, which are much more like a component. I think you can look at, and it's got interfaces you know, and it's not an object, it's just a service provider. So components became more popular as people saw the shortcomings of remote objects and the sheer complexity of dealing in that world. If you think the APIs is difficult for the stuff you've got to do in the lab, Corba was a bit worse than that. It's a C++ view of what you should be doing there. And the other thing that killed Corba was this guy. So that particular world, that sort of Sun-based Unixy world, went to Java, and although Java uses bits of Corba stuff underneath, it became Java and J2E took over from the nascent Corba market. So that's what happened there historically. But so Microsoft had a component model, DCOM, which is still floating around, and you're using WCF, which is another Microsoft implementation of this type of componenty thing. And This stuff is probably, well, nothing wrong with it, widely used, particularly that one's still sort of current. That morphed into, some guys, particularly one called Don Box, thought, hey, XML is great. Yeah, we could write a simple remote object methody thing using XML. Because the trouble with some of these things is firewalls. And people lock down systems. And great, no, you can't have a port for that. We're not opening up our firewall. But everyone has port 80 open. So if we can write a remote object protocol which sits on top of HTTP, hey, we can get through the firewalls. So that was the initial reason for developing the first versions of SOAP. So SOAP is simply a version of one of these types of things written in XML. So you saw the XML we just had, that's what SOAP is. And it's firewall friendly, which you may think, if you're a security person, is totally negating the whole purpose of a firewall, but that's just being pragmatic. And then SOAP morphed into, well, so the S in SOAP stands for simple object access protocol, I think. But the S stands for simple. And this is not simple, it's rich. Now, rich both means mind-bogglingly complex, but it also means it does all the things you need to be able to do. The standards there for distributing transactions around your system, the standards for security, the standards for discovering objects, etc. There's a rich set of services along with the basic remote object invocation protocol. And you need them. These guys have the same type of rich set of services. SOAP, which is sort of sitting in about here, doesn't. It just says, here, go and call something. Here's an HTTP message, go for it. So it doesn't have all those rich ancillary services. So people thought, oh, that's cool, we could do them. We could go and build a complete distributed computing platform along the lines of these, using SOAP as the fundamental method calling and providing support for distributed transactions and security and etc. So a complete, fully functional, full fat distributed computing environment, but based on possibly running over HTTP. SOAP is agnostic about the transport layer. You could send SOAP messages via carrier pigeon if you wanted to. The marshalling and unmarshalling is writing bits of paper, but you could do it. It doesn't care, but normally HTTP, and all XML based. So an XML webby sort of thing. And that is what web services are. The WS star web services set of things, set of standards, is in that world. Now that upset the web community, meaning the HTML jockeys and people who are writing web pages and things, because they say, oh, that's not really web-like. Web-like means this. Oh, you guys don't know what you're doing. Look, we could do simple request response things just using HTTP, using the standard HTTP verbs. And that gives you rest. Of course, if you want the full set of services, then you need to wrap other things around it, but that's life. We'll be returning to those things later. And there are other protocols which are around. There's various message queuing protocols, which are really useful bits of infrastructure. They have interesting properties, some of which are repeated in here because it's full strength. So that's the history of all this stuff. So your question was, why do we have them? Well, historically, why do we have this rather than everyone using that? Because these people looked at this and said, oh, my God, that's complicated and it's not very webby. I want to do something webby. You're misusing the word web. So there's two different cultures clashing there. And now you look at them and we're using bits of this and bits of that. And as I said, when we look at one of those complicated balls of string, not all the wires will be the same. So some of those wires might be some of these things, some of them might be this, some of them might be that, some of them might be that. Because each one of those has its own useful properties which the others may not have. The message queuing, for example, I'm using MQ because there's a whole lot of things which are MQE in their acronyms. There's IBM's MQ, there's MSMQ, there's Java messaging. They're all the same type of thing. And they have a great feature of they're both asynchronous, which is useful for some things, and you can configure them to be resilient and robust. You say, send that to Fred. It says, okay, I will send that to Fred. If Fred isn't listening just now, I'll try that Fred every now and again, and I'll guarantee I'll try for a week to send it to Fred. At the end of the week, it may time out and it says, I couldn't send it to Fred, but it's better than you just saying, I assume Fred is there. Here, Fred, have this, when you have no way of knowing. So that robustness and resilience in the message queuing is a really strong feature. So that's why you'll find parts of the system may be built on that. Message brokers. They're tied into that. So when people were building these types of systems, you start noticing patterns. I write code that, I need a bit of code that takes this type of message and reformats and sends it out to there. Or does these simple transformations or some logic that I could explain to a manager with a flowchart. So those types of common functions get put in, and you start getting these message brokers, and their job is to act as a bit of glue and routing and transformation to save you a lot of that boilerplate, boring code. And they, again, pick up functionality and things.
So that's underlying the message broker.
Yeah, exactly. It's a application thing built on top of some of those protocols to do common things for you so you don't have to do them yourself. I added a slide here with distributed architecture. These are all both the diagrams of distributed systems. There's the top one is a distributed system built up from components from different organisations, perhaps different parts of the same organisation. It's primarily peer-to-peer. The retail application talks to shippers, and the relationship between the retail application and the shipper is peer-to-peer. They're both independent organisations. It's a peer-to-peer communication. There's no inherent layering here. All the participants are peers. They're all equal. Some may be more equal than others. And so lots of potential lines there, but there is peer-to-peer. And that's what we have supply chains and we want to do, validate this credit card, etc. They're peer-to-peer messaging. But we also have distributed applications like this, which is layered, tiered, where we say, okay, we're really only doing one sort of application, and we're going to distribute it amongst different bits of our, different physical bits or different logical bits of our system, and we're going to do strong layering. So we've got a client tier. There might be multiple different types of client tier. Web pages, running on client systems. We might have some rich client apps somewhere. We've got background processes doing things like printing invoices, etc. That's all up in the client tier. And then we've got a business tier. There might be multiple invocations of those. And then we've got some type of data tier. So the applications you're playing with in the lab tonight and playing with last week are distributed applications because we've got multiple processes and we're doing things between them, but they're strongly layered. And that layering is not visible in that top diagram because it doesn't exist. But here, it's a different type of distributed model. Here we've got architecturally we're putting layers in to make it easier to know what goes where. So we know where the responsibility of any particular type of thing lies. So this is something to do with the data and maintaining access to the data and transforming it. Oh, good, it lives in the data tier. And then within the data tier, we can worry about replication and failover and things. But those concerns are purely within here and not over here. And similarly, we know the business logic is all in here and is not leaking into there or there. So we're distributing it, but we're reflecting that distribution in terms of layering. And the top one, each one of these things up here could well be like that, but that's not visible at that level. And the types of wires connecting all these bits would probably be different to the wires connecting those top bits. So, distributed computing is really fun, just like ordinary computing. No trouble at all. Interesting new failure modes. So, we want to call something. Cool. We have to traverse a software stack. So we call this and it calls that, and then turn it to a driver. It's got to go physically out through a network interface card. It's got to go onto a LAN. It's got to go through switches. It's got to go out onto public networks, perhaps. Speed of light is a real nuisance. It's really slow. There's not much we can do about it. What's the speed of light in glass? Speed of light in a vacuum. I'll ask it easier for you. Speed of light in a vacuum. 300,000 kilometres a second? 3 times 10 to the 8. Yeah, 300,000 kilometres a second. It's about 2/3 of that in glass. Why am I interested in glass? Because fibre optic cables are glass. So about 2/3 of that in glass. How far away is Canberra? 300 kilometres is the answer to that question. So how long does it take a message, ignoring the switches, etc., how long does it take a message to get from Sydney to Canberra? 300 kilometres, 300,000 kilometres an hour. It's about 1.5 milliseconds. So, milliseconds-ish. So if you're talking to a remote computer in Canberra, it's going to go in the order of a millisecond or two just to get to the computer, just because of the speed of light. Speed of light sounds very big, but when you start doing hundreds of kilometres, it starts getting large. People still, unfortunately, use geosynchronous satellites for communications links. I say unfortunately. A geosynchronous satellite. You know geosynchronous satellites? Here's the Earth, here's a satellite. And it's geosynchronous because it stays above the same point on Earth. It's in an orbit above Earth, but it's staying in exactly the same spot above Earth. So geosynchronous satellites, which is what you use for most of the comm stuff. They're 36,000 kilometres above the Earth. And you do that, how long does the light in a vacuum take to get to there and back again? It's an unfortunate number of milliseconds, tens of milliseconds. You can do the calculation. And you've got to do both ways, right? So you've got to go there to the satellite and back again. So your round trip is 72,000 kilometres. So work out how long it takes to go 72,000 kilometres at the speed of light, and it's an unfortunately large number. It's 72,000 over 300,000, and that's of a second. So significant numbers of milliseconds. So if I'm doing a remote method call, my remote method calls now take milliseconds at least, rather than, they're going to take in the order of milliseconds, not microseconds or nanoseconds. Calling something locally, I can have very chatty protocols, and it doesn't matter. I mean, lots of backwards and forwards because they're all really fast. If I start doing that remotely, that's going to really hurt. And all types of interesting new failures. I can have lost messages, messages can be delayed, messages can arrive out of order. Because if I say I send 2 messages to you, 1, 2, they might go via different paths in the network, and they might arrive in a different order, the order I sent them in. You can't get those type of problems if you're doing something locally. I call this, I wait for response, I call that, or I do another call, and they'll always arrive in the same order as I sent them. That's not necessarily true in a network. So now I have to worry about message ordering. So my protocols might want to have a message ordering thing in it. Perhaps my lower level protocol takes care of that, perhaps it doesn't. So lots of interesting networky issues to worry about. And I can have partial failures. This part of the system is working, that part is not working. So now how do I cope with partial failures? Lots of interesting challenges. So my applications, although theoretically I'm trying to make it all transparent, in practice have to be really quite network aware because they have to cope with the failures. I do a method call. Locally, I haven't got to worry about an exception coming back saying that method call didn't work. In fact, there may be no way of getting an exception. Whereas in this world, I do a remote method call, I have to be prepared to get an exception because it may not work. Or it might time out, things that I can't handle. And I particularly want to worry about network round trips. The standard OO model you see where I've got some object and it's got little getters and setters and one line, I call something and it does one or two instructions and then returns because they're really cheap. I can't do that across a network. That's not taking 5 nanoseconds to get that value from that object. It's taking me 5 milliseconds to get that value. So an application which is working fine locally, all inside the same box, if I move that object to be remote, it might just be a performance disaster. Nothing wrong with the code, it's just making assumptions about the latency of the calls. So very fine-grained, small objects, very small method calls are really not a very good design principle. Even though they're a common OO design model, they're a really bad design model if I'm going to do it distributed. What instead I want are nice, meaningful, coarse-grained chunks. The transfer this money from that account to that account, complete operation. Not do this little bit, do that bit, check this, check that. The client should be calling on the server to do a large, meaningful chunk of work. So therefore I'm minimising the number of round trips. Evolving distributed code. So you want to add an extra method to an interface or an extra parameter in an existing method. So if I've got local code, I just go and make the change, push build, boom, it's okay. If I'm doing it on a production system, perhaps I've got to go and stage the updates. But in a distributed system where there might be clients scattered around the world, all of a sudden, if I just made all those clients incompatible, how do I evolve my system while maintaining compatibility with an unknown number of things? And of course, people say, well, we just do it all with JavaScript these days, and we just download the new client every time we do an operation. You possibly could, but you can do it by having immutable interfaces. So this is this interface, and we version it. It never changes. There's some magic little version flag. You're a version 1 client. We continue supporting version 1 clients. We go to version 2 clients. Version 1 clients still work because we have some little magic that says you're a version 1 request, I'm a version 2 thing. We can sort it all out. So versioning is your friend there. It's better than trying to go and find every possible caller and change them. So you get immutable interfaces, and you can see this with some of the frameworks you use and some of the operating system APIs. The APIs have the same problem. Microsoft or the Java community defines an API for something. Boom, there we go. And now we want to change it. You can't change it because there are people who've written client code. These are breaking changes, and all of a sudden their code won't compile anymore or will fail. So then you have to go and do versioning of those interfaces. So you see interface EXT on them, which is we thought of a better idea, and here's the extended version of the interface, but the old one is still there. And it stays there possibly forever. Or you deprecate it. That's the official word, deprecate it, which means we're telling you not to use this, and at some stage in the future, we're going to make it go away. We're giving you fair warning that it's going to go away. The company I used to work for with their operating system had a great feature, which is the opposite of what Microsoft and IBM do, which was they would stop running old code. The operating system would release X, and it would only run code that was compiled on, say, X-2 up to X. And X-3, I'm sorry, that code's too old. So they deliberately broke stuff and gave you warning that it was breaking, but that let them evolve interfaces over time. But they still had the problem that they had to maintain 3 years of compatibility. So the lessons learnt from all that. So transparency. It's really just to do with the programming paradigm, the model presented to you, so that you can see that you've got method calls rather than messages you have to construct in some complicated way, and you don't have to know about the networking interface perhaps. So you can continue thinking in familiar terms, but remember that although the technical complexity is hidden, it is still there, and you're going to have a lot of care has to go into thinking about failures, thinking about the exceptions, thinking about the implications of things like latency on performance of your system. So if you're going to build a reliable, fast distributed system, you need to know all the problems that come with being distributed, the pitfalls, and then there are technological aids that will help you there a lot as well. So not only will your frameworks provide you with the exceptions, but there are tools like reliable messaging layers, distributed transactions, perhaps something might automatically do failover, so configure your system so that the service itself is replicated and will automatically fail over. Stateless is good like that because if a box which is running those stateless servers fails, another one can take it over because nothing much has been lost because the state's kept on a state server. So you can put a bullet through that particular server box and it doesn't matter because another one will take over the load. So there are techniques to make life easier for you there. Okay. Probably actually going to finish a little bit early today, which is good, rather than having to sprint over and be late for the tute. So the next set of slides are talking about some of the stuff we just talked about in the Java EJB context. They're not talking about it in the Microsoft context because you're doing the tutorial in that context. So you've got code to play with and to try to understand there. But it's very, very similar. It's all looks complex, and it is, but that complexity is sort of inherent complexity because you've got a lot of things you want people to do. So programmers want to be able, and architects want to be able to do this. They need to have that for that functionality. So you've got to provide interfaces to let them do it. If you didn't do it, you said, oh, what you want to do is really simple. Here it is. Here's your one solution. Now, someone will say, well, it doesn't do what I want to do. I need to do this as well. I need to be able to substitute this protocol for that protocol. I need to do, so in order to cope with that flexibility, the APIs you use, the frameworks you use, are quite complex, but a lot of that complexity can be ignored because the defaults are pretty good normally. So, the Java world here. So, J2E, which is what killed off Corba, provides support for tiers. So, those tiering models we saw both work on .NET with the technologies we've been using in the labs, but almost identical stuff will work on in the Java world. And it's meant for, the whole frameworks are meant to support those types of applications. Inherently complex, yes, because you've probably got a complex system. You've got lots of data types, lots of client types. So the architecture is going to be around controlling that complexity, but giving you the tools to do it. We'll typically do things in layers. If you've been doing them in the prac, client tiers, web tier running on a J2E server, business tiers, and some type of enterprise layer. So that looked like the type of stuff it did in the prac, except the names are different. So the diagram that you had with the multiple tiers for the prac in the first week is the same type of diagram as that, except this is from a Sun Oracle Java world and the other one was from Microsoft world. We call these things enterprise beans rather than business components. That's the case, just a word change. And we have JSP pages rather than ASP pages, and we have a EIS tier rather than an entity tier. And so in the world you've been working in, that's enterprise framework, that's ASP, and that's the business layer. But exactly the same model, just the words have changed.
EIS.
Yep.
EIS stands for?
Sorry?
EIS stands for what? EIS.
Oh, Enterprise Information System, I expect. If you're really good, you can have multi-layer acronyms. Well, some of the letters stand for other acronyms. The TLA is a 2 or 3 layer acronym. Okay, so we've now broken up that the business tier. We've got entity beans, we've got session beans holding a session state, message-driven beans for taking requests, and we've got that web, this is the server-side web code, and Java components over here. Client tier, that's all pretty obvious. So anything interesting in here, we've got the magic word stateless up there. So this is a stateless bean. We've got class calculator service. It's implementing those two interfaces. Defining the sets of methods that are supported by this. We've got calculator service, add, divide, multiply, subtract. They're all pretty obvious. That's interface definition, those 4 numeric operations. So I said before that you might have some abstract definition of an interface, and it's going to be turned into generating stubs and proxies. Well, in the Java world, that would be an interface definition. So, you want to go and call something with this interface, I know what my method signatures are, because it's getting from that. Now we start getting complicated. So, what are some of the things in here? So in this world, have I got a slide on that? Let me see if I can just... Yeah, that's the slide I want. One of the things in the Java world is a thing called Jindy, which is a directory. So directories are things that hold things for you. And amongst things that can hold can be instances. So you say, I want to find something or other. So you can do a call on Jindy and it will go and be a directory to tell you where things are. We've got a protocol, RMI, method invocation, the top ones we were talking about before. And that's an ORPC protocol. We've got Java messaging service, which is a message queuing type interface. We've got transaction support, and we've got a low-level database interface, which will probably be subsumed in entity beans. So, if you like to. Say in there. Environment, factory. We're defining where our provider is going to be, localhost 1099. We define the endpoint for that, create a context, and then we can go and look up the service and call it. In the .NET world, that thing would be a config file, an app.config file or a web.config file. You often want to, rather than writing everything in code, you want to have an abstract configuration definition of things which is separate from your code. So you can just go and change it. When you deploy it, you provide a new app config appropriate for the deployment, without having to go in and change the code. This is an example of one of those. So that's defining the jar, the archive, enterprise bean, there's some properties of the session, the stateless, container transaction type, describing the assembly, method interface, transaction required, so just attributes of that particular interface. Done that one. Okay. There are some slides on this, but I've hidden them because you're going through it in this week's lab. Speaking about labs, how are you going with assignment 1? Task A1. Which, as you know, is due at the end of this week. Due Sunday. Is that a surprise to anyone? So, I assume the tutors have talked about this. So, you've got an application, and you've got to extend it slightly. And the very first part of it, which is worth a whole 1 mark for the course, is just telling us what you're going to do. Give us a new data model, which will support that functionality, and tell us how it's going to work. And the reason that's due before the rest of it is so we can give you a solution to it. So it's really just a matter of thinking, how do I do that extra functionality? And just give me the model that will do it and say how it works. Do you all remember what it is you're supposed to be doing? I want you to do a simple recommender system. So people can look at books and they can buy books. And now the new functionality is on books that they have bought, they can like them. And then you can show people what books that people who liked this book also liked. Okay? Recommender system. So if you liked book X, then you think, oh, I wonder who else liked that book. What did they also like? Because that might be another book that's interesting. So that's what you have to implement. Have any of you thought about what the data model changes are yet? None of you? Okay. The assignment submission, I think, will be open from tomorrow morning. I think that's the date I put in Canvas. Alan did something to it afterwards. So, and it's due at the end of the weekend. And then we'll put up a solution early next week. And the idea of us putting up a solution is then you can treat that as feedback and go, oh, I got that all wrong, or oh, yep, that's fine, that's what I was expecting to do. So we're giving you 1 mark just as an incentive to do the first bit of the work first. And I suppose we want to talk about how, have any of you thought about how you change the data model? Who has thought about it already? Okay. Oh, 1, 2, 3 people, good. How many more entities do you need to add to the system? Any idea? 1, 2, 3, 4. Anyway, so that's the first assignment, and we'll give you a solution to it next week, and then you can go and do the rest of the assignment after that. Right. So it's all taking a little bit less time than I thought I'd take to go through those slides. Okay, let me look at that. Okay, we'll do some of these. So that's that same diagram as I was hand waving about. That's the .dat version of that same diagram. So instead of entity beans down here and component beans here, they're called something else, but they're the same type of thing. Those cross-cutting things, security, they're all common. And there's a version of this diagram I'll put up in a few weeks, which is the web services version of that, and it looks almost identical. So we've got those things are now coloured stripes going vertically in web services stack as well, because it's trying to provide the same type of services. These layers are purely a convention. You might get some support for them, but they're not in. You might get some tool help to help you build them, but they're not inherent in the technology. The technology just lets you go and call things, but the architectural stuff is a convention. People decided that layering is a really good idea because it reduces the complexity, but it's only... So there are tools to help you build this. There are tools in the development environment that you go and draw petty pictures of entity diagrams and draw lines between them and talk about this is a one-to-many, etc. relationship, and then push a button and what pops out will be that type of thing for you. There's no reason why you have to do that. You could write a piece of business logic and just go and call a database interface yourself. But if you're wrapping stuff in objects, then why don't you have a business entity layer, an object layer there, and build code that will help you build that automatically. Particularly in the bookshop example, these are quite complicated because that's the way it's done. There are inherent complexities there and complexities there because of the way it was done, and complexities there which are complexities because they look complex, but they're actually code you don't. You see all these files, and you think, oh, what are they all there for? And we'll find one. There we go. If you go and look in the solution view here, and you see all these files, and of course most of them you don't write. Most of them are generated for you. So Matt, when he built this example, didn't go and write all that code. He wrote very small bits of it. But he did push a button which says, go and generate this for me. And he was very fond of a tool called AutoMapper. So when we do have those types of layers, we tend to have mapping between the layers. So, we've got these type of objects here and these type of objects here, and we want to map between them. So he's using a tool called AutoMapper, which will generate the mapping between those objects. So, but a lot of that code he's not actually writing, is written for him. So, I might as well go through this. This example is an extension of the one which you did in week 1 tutorial. And it's the same entity model as you're used to, except Matt decided that he wanted to be able to have specials. So a particular media could have a genre, and you can place particular genres on special. Let me unhide this. If I do that, there we go. So to support that, there's your media object, which is very similar to your. The only change is it's got a director rather than an author, from the one you've got in your book example. And he decided that what he'd have is an object which is genre. What's the relationship between genre and media? What's the manyness of that relationship? 1 to many? 1 to many. So each media item is of a genre, and each genre can have many things in it. So there's a 1 to many relationship between these two. And then he decided to have a separate special entity. So things can go on special. Specials have a discount price, a start and an end date. So what's the relationship between these two? It's sort of a trick question. Well, yeah, so I would say it should be 1 to 1 because, yeah, so what's it mean to have more than one special record for a genre? And can they overlap in time? Does that make sense? Do you care about previous specials? So if you've got, because they've got time in it and they cover a time period, do you want to have multiple special records, or is it really 1 to 1? If it's 1 to 1, why do you have a 1 to 1 record? Why not make them the one? So if I go back to the assignment which is due on the weekend, I've got recommendations, so people can like a book. So what's the relationship between whatever liking, wherever like is held, like, dislike, that thing, what's the relationship between that and a customer? They can have many, right? They can like many books. What's the relationship between a book and a customer? Customers can buy many books. Books can be bought by many customers. So that's a many-to-many relationship there. And often when you're doing these types of designs and you've got point it out here, that's cool. So these are all convenient, you've got little ID things in them. The ID I can use as a foreign key. So if I have a one-to-many relationship between something and something else, then I implement that physically on the many side by having the ID of the one side embedded in it, the right way around. One to many. So yeah, so I've got media and stock. I can have multiples of these, but each one of these refers back to a single one of these. So I've got a media ID in each one of these records because it's one to many between those two. If I'm doing a many-to-many relationship, then I can't have that. I can't have a list of, with relational databases, I can't have lists of things in here. There are older type of relationships where I can have lists, but I don't. So I can't have a list of things in here, and I can't have a list of things in here. So I'll implement a many-to-many relationship via an intermediate entity. So I'll go many to one. So two many to ones gives me a many to many. And that might be exactly what you want to do for that assignment. But here it's all one to many or perhaps one to one, depending on how you want to interpret having more than one special record. And I can't see any way that makes any sense. But if you want to have historical records, but then you've got to keep the most, when I'm going from genre to special, I've got to find the most recent, I've got to find the special then which is current. So if I have multiple specials, how do I find today the one which is in effect today? So I could do it, it's more code to write to take today's date and find the specials record, if one exists, which applies to today's date. So that's another reason for only allowing one special. Then if you want to update a special, if you want to have a new special, then when does it apply from? How do you get it to be picked up? So perhaps you want to have multiple specials and have the code to work out which ones apply. So, very good questions. So what he's done here anyway is just put in a special and a genre record. And then he would have gone over to this side and pushed the magic button which says, okay, I've done my entity model, go and recreate everything for me. And it would have created all the entity objects, all the things in the entity layer automatically, and generated an SQL file which will implement that database. So what you've been doing in the labs is creating a database and then opening the generated SQL, which will go and create a database that implements that model. But that SQL again is created automatically. So all that Matt did was go and add some things to this diagram using the diagramming tools and then push the button and then delay got created.
So the expectation is an AI model like this, or is it says UML diagram?
Sorry?
In the assignment it says the UML diagram.
Oh yeah, sure. Because he wants they just wants a nice diagram of it, and UML will do. Yeah, but that type of diagram would do me fine as well. But I just want to know what the entity model is. Yeah, but presumably UML models was an acceptable way of doing it. So you can do entity models in it. So that's fine.
Should we explain ourselves? Maybe a small write-up or something.
Yeah, what it says is I do want to know how you are planning to do it. Yeah, I think you'll find the data model is very simple. The code to make use of the data model is not as simple.
We don't have to do the code by
No, but it'd be nice to know how you plan to use. You've got to justify your change. Yeah. This is where we start getting complicated. This stuff's fairly straightforward. There's a business layer. We've got multiple externally available components. We've got catalog, stock, user, etc. And there's obviously some predefined interfaces which are over there as well. My catalog provider. So catalog provider is a type. Interface catalog provider. The I in front of it just is a convention for interface. So we've got an abstract interface for catalog provider, and this is an implementation of that. You know about interfaces? Yes? No? So it's not object inheritance, it's interface inheritance, which was when components were coming in, the religious zealots who were pushing OO said, oh my God, it's not pure. You haven't got inheritance right, because they did interface inheritance, not object inheritance. That's different. But so this is catalog provider implements the iCatalog provider interface, and it's got two implementations for two methods: get media items and get media by ID. And this stuff is link, is a data accessy languagey thing called link. The message types going to the outside world. This is the mapper stuff that he likes using, which generates messages from object definitions. Service contract. This is an abstract definition of a service contract. The outside world, WCF world, is going to be able to call in. So this is the abstract definition of the contract. So I've got a service. The outside world wants to know about the service, what services it provides, how to call them. That's one of these. So I talked about abstract definitions in something like an IDL or WSDL. This is the C# version of that type of thing, and it may be that when you push a button, you'll get a WSDL version of this produced. You can ask for a WSDL version of it because you might be accessing this through a web services interface, and the web services world uses WSDL to define these systems. So you can translate from that and generate a WSDL XML version of the same interface. These are, what do they call them, decorations, attributes. So this is just telling the compiler that this is an operation contract. It's not part of C#, it's decoration around it. And implementation of it. Now I'm going to go to here. No. There we go. That's what I want to get to. There is I said that there are sort of a lot of stuff looks complicated, and if you skip through half a dozen screenshots of you have to change something here and change something there and change something there, and someone had to create those things in the first place, even if they were automatically generated as skeletons, you've still got to populate them. You could also say, go and do it for me. So if I have a service running somewhere, and I know I want to go and invoke that service from Visual Studio, I can go, I'm in this client, presentation layer, in my web client, I say add service reference, I click on that, and it comes up and says I can either go discover if it's all inside the same solution, and it will go and look inside my solution for all the services I've defined, just go and search for the appropriate interface and say, oh, here's what services you have, or I can go out to a network and look for it. And this is local host, so I've got catalog services running, so it'll go and look for the metadata service from that service. And if it finds it, it will go and generate lots of stuff. So it goes and searches for a service definition and says, oh, okay, all that plumbing you want, I'll just go and generate it for you. So it found an abstract service definition in my solution or on that particular server, and then went and generated lots of that plumbing automatically for me. And this should look pretty similar to that Java example we had before, except it was in a different syntax. We've got services, we've got so two things interesting here is catalog service, we'll pick on this one, and we've got both metadata and the actual service itself. The metadata is how when we're doing the service discovery, that we pick up the interface definitions and method definitions. So we've got that metadata being exported as well. And it's in that one, no, not in that one. So do that, get those screens to pop through. And generates that automatically. Yeah. And go. So that's an alternative way of doing it. So the idea is generating a lot of that plumbing for you without you having to write it by hand. In the case here, the plumbing's already been written, so it's easier for you to just drop pieces in appropriately to extend the application you've already got, rather than starting again from scratch. Okay, that's.
Will you be sharing that deck?
Sorry?
Will you be sharing this deck with us?
I can republish the slides.
Oh, I see.
Yes, they're in that same PowerPoint. When I did the PDF, I don't know whether they came in or not.
I did not see this one.
Okay, fine. Because I hid them, so I wasn't sure whether the PDF would produce them or not. Yeah, I'll just put those on. I'll do this as well. Okay. So any other questions? Or you can get off to your shoot on time today rather than 10 minutes late. So in today's prac, you should be a fairly straightforward prac today because there's a prac for weeks 3 and 4. And two purposes of it. One is to understand the stuff the distributed transaction stuff. It's a much simpler application than the previous one. And there's two parts. The first one does not use distributed transactions. And the next week we turn distributed transactions on and we do the same thing with distributed transactions. So you get to see what happens when you have distributed transactions, and if you don't, data goes missing. So two parts for it, but the real purpose of it is to not only do the DTC stuff and see how the transactions are working, but also look into some of the distributed computing parts of it as well, because it's a simpler application. Okay. Right, see you next week. just need one entity. Using it is more complex than saying to what to do.
So we have to explain how message types will be using that entity.
No, so this first one is just another entity or more than one entity. And I just want to know how you're planning logically to make use of that to generate this sort of recommendations.
So sort of explain the business logic.
Yeah. So when tell me how it actually works. Because it's fairly complex. Because the entity extension is probably trivial. Trying to make it look nice is probably hard. It's just to get you started early, and so we can say, here's an answer. So in 3 weeks' time you're not going down the wrong track. And if we make it work A mark, then people will do it.
So last week during the lecture we talked about there are 3 different kinds of state. They're like local computation state, resource state, and so session state. But then in the tutorial sheet there was like an infrastructure state, which infrastructure state. So
okay.
And I was like pretty confused about it because I'm trying to find on Google and I couldn't find too much helpful info.
Well, there's all that configuration stuff.
Oh, so that's
Okay, I suspect that's what they mean by it. So if you so infrastructure would be things like your messaging layers and now where does it say that?
so local computational resource session and infrastructure.
Yeah.
So
I left that word in. It would be configuration stuff.
okay, cool.
Yeah.
Just to double check.
Yeah.
Thank you.
Okay, so do you only need one UML for practical task A1?
Two. It says two.
But the message type is automatically generated from from entities, right?
Mm-hmm.
So what's the difference between the two UMLs?
Well, not necessarily for the outside world. So there's an entity model saying what do you need to change at the entity layer to support the function. Do you need to change anything at higher layers as well, apart from the code? So is it going to affect any of the messages being pushed out in any of the interfaces?
Okay. So what's the difference between the UMLs? So
What's it actually say? I've got a copy of it. You got a copy of it there?
oh yes, right.
Asking the same question?
Somewhat similar because in the practice sheet it says they want UML and you're mentioning like we can do ER diagram just fine.
Yeah.
But then like they also said they want it says it wants methods as well.
Okay. Right.
So
Right. Right. So if you have a look at these, so you I think I'd implement the entity. I've got to just add one more entity.
yes.
But what I don't know, because I haven't written it yet, is whether at the services level, message types, whether are those recommendations surfaced. So when you're saying look at a catalogue or look at a particular book from the catalogue, if there's a message type for that, is that recommendation list now out? Have you got extra data at that interface level? You're supporting recommendations now.
Yeah.
It's something
So-
like the class diagram
Well,
in the property.
so that one's at the entity level. Okay,
So this UML is
But-
basically.
so this is the message types. We've got where is our message types?
Has many
we'll
class
get it.
in it.
The message types.
Yeah.
The message types are automatically generated using the auto-mapping, right? It's
I don't think so.
Yeah, sure, but they're coming from somewhere.
message types are down here.
Message types.
There are many classes in there.
Sure, but they're coming from some other definition, right? So
One class
You
is
look at, so again, look at message types.
This is the interface I get, like the abstract
Okay,
class.
Right, that's just the abstract one.
Yeah.
Um,
It's touch screen as well if you prefer that.
okay.
And all of the other ones are like implementations of that.
And I'm actually not sure what this message type is for. It's just an ID.
Let's look at some interface.
So interfaces.
So, yeah, so are we going to have to change some of these things? So we go back to services. Services. And catalog services.
Yeah.
Yeah, very sensitive.
Oh yeah.
Get used to it, I know.
I usually use the mouse actually.
That's okay. So I've got a screen. So how am I going to present this recommendation to my user? So I've got a presentation layer, and I now want to be able to let the user say, find more books that I might be interested in.
Yeah.
Now, that's something happening in the presentation layer,
Uh-huh.
and it's got to make some type of call down into the service layer to get that information.
Uh-huh.
And how is that information passing through that layer?
Message types.
The model, the MVC model.
So if you go and look at the way we do,
This is
Okay.
probably better. And this is still a bit more set.
I think the service interface is difficult to understand.
So
Yep.
are we just
but if we
drawing a UML for these all these classes, or
Probably need new
Well,
ones. Because medias is for
you need
books.
something, because we're surfacing more functionality. If I go to the UI,
UI is in view
find
folder.
the UI.
These are
View.
probably view models and view
Yep.
done there.
So which of these will be modified to show
The
the
model.
recommendations?
I think they would want catalog view to have a button to like or dislike, and also they want a
Yeah.
detail view as well, where you actually see
Yep.
the
Yep.
extra
List of,
recommended books.
yes,
Yeah.
a list of recommended books. So how does the user interface get that information out from the...
It's probably like when you open the web page, it'll sort
Yeah.
of send a request to the service layer.
Yes, to the
service
service
will
layer.
return a new
And-
message type with
Exactly.
the recommended books.
Yes, exactly. So we just said that you just answered the question. So at that service layer, we
got that
need
part
some
yet.
way of surfacing that list of recommended books. So whether it is of, I don't know what the message is going to look like, but we need some way that the user interface layer can say, here's a book, tell me other books that are recommended like it. So that's
Yeah, that makes sense.
a service layer thing. It's not the underlying entity in the database. It's a function built on top of that.
Yeah.
So you think you're happy?
I'm still confused.
So we've got, let's do 3 layers.
Mm-hmm.
Oh, I'll use that. And there we go. Oh, fantastic. Good. And there we go.
Yes.
All right. So
This work as well. You prefer that.
so we've got a new entity,
Mm-hmm.
which is
A table or
a new table.
Yeah, in database.
In database is a new table,
Mm-hmm.
right? And it's going to be where we actually store
Mm-hmm.
the information about likes and dislikes.
Relax.
Okay.
Okay, so let's talk about what that would be. It's pretty straightforward, so let's talk about what it would be. So one rule is that you have to have purchased a book before you can like or dislike it.
Mm-hmm.
Okay, we don't keep track of purchases just now. There's no entity there.
We do.
Where?
The orders, I think.
order item.
That order is stuff that you've ordered.
Yeah, but then that's the thing you purchased. Right? So you mean for
Also-
purchase there might be a separate purchase table?
It could be. Because orders are things which they have a different function in the system. So you could possibly tack it onto order, or you might say order is something which is just there. Do we delete orders after they've been filled?
So I guess it would make more sense to have another relationship directly between users and books for purchases, sort of.
I could it might be sort of the same as order, but it seems like it's wrong for it to be order.
Yeah, I guess like the query itself, if just based on order, would be more complicated because you have many orders to go through to find the different books. If you have direct connections, that would be like faster in terms of database queries and stuff.
And do we have the appropriate linkages between orders and books and users and things as well? We might have the relationships may not be there.
I think let's just grab
think
the
it's,
that one.
Yeah.
If orders and order item.
Order items and order item.
Like you have
It's got quantity.
And item ID.
Get used to a laptop after a while. Scrolling is really easy. You try another one really hard.
So I added this myself.
Okay.
So you can just ignore it.
Yeah. So perhaps what's the relationship between that and where?
Between rate and user. So rate is.
So
Well, actually no. So order item is associated with order, and order has customer ID in it. So order item is associated.
an order is effectively contains a list of
order
order
item.
items.
Yeah.
So there's one to many between order and order item.
Yeah.
So order can't be where you want to store the like and dislike.
Yeah.
It's a one to many.
Order.
it should be
The
separate.
order item could store it.
Yeah.
But it just seems to be functionally wrong. But you probably could, because it might, whatever you have, if you have a rate, and a rate is many to many between media and customer, isn't it?
But you have
So-
to
So customer,
you have to purchase something to rate it.
Yeah.
So it should be associated with order item, I think, because you have to purchase it. You can't just rate something.
But you can put that into like business logic to check that, right? Like in database, you can have the rating connected to user and connect to books, but like in business logic layer, like you cannot rate like it if you haven't purchased it.
To
Like-
some authentication.
Yeah, that's what I'm
So-
thinking of doing.
it's good. So we could
So yeah,
reuse.
there are multiple ways to do
We could reuse order item.
Uh-huh.
My problem with doing that is it seems wrong.
Because order
Because
item is not supposed to be.
it seems to have the wrong type of lifetime. It might be where we want to record the fact that you have purchased it, or we could just have a thing like you've got rates there, which is sitting in between a user and a book. But when you purchase it, you might have an item there which is just once you purchased and the purchase has gone through. So perhaps orders are things on order which may or may not have been delivered, and after the delivery process we create you own that
Okay.
record.
Interesting. Okay.
Anyway, so go back to the layers. So we have down here something which is where we're recording the like-dislike status, and it's in between a customer and a book. So if we implement it as one of these two one-to-many relationships, so it's effectively many between customer and book, and sitting in between, the glue in between the many, is this person has purchased this book. So that's the way we normally do many-to-many, by having an intermediate object, intermediate entity, where you go, which has two one-to-manys, and it sits in the middle. So that one, which is could be one-to-one with order item, if you want to conflate the two things, but you may not want to, because conceptually they're a different type of animal. Because your order items disappear when an order has been fulfilled.
Yes.
There's information about order items. It just seems that an order item has something to do with the ordering part of the business and the fulfillment part of the business. It's just a different part of the business.
Okay.
And perhaps that these things sitting in between here might be one-to-one with those, but they may not be as well. They might have a different lifetime.
Okay.
But that's a design decision to make.
Okay.
But wherever it is anyway, we've got something down here which is recording that this customer has purchased this book and has liked it or disliked it. We've got a new entity there, or order item is holding that additional information. Doesn't really matter. But up here, at the user interface level, we want to be able to say, given this book, find the other books that have been liked. People who like this book also like that book. So at the service layer, we need to provide that functionality so that the other layers can call on it to present the user interface. So we've got a layer here which is just the entity layer saying, what are we doing down here to make the change? And a service interface layer up here so the UI can call on that to get the business layer to go and construct the list of recommendations. So that's two things.
So we're trying to draw UML for this part.
Yeah,
right?
a UML for that part and a UML for that part, the service layer, and a UML for the entity layer.
Oh, but so we're just drawing UML for message type.
No, we've got to have one for the entity layer as well.
Oh, really?
To add.
Yeah, just two. But you know, what changes are you doing to the entity layer? What layer?
So this part is.
Entity
So
layer.
this
Entity.
this is entity.
Exactly.
Ah,
Yeah.
okay.
Yeah.
So that's so the difference is kind of okay.
Well,
Yes.
one of them is just a single piece of data that you're adding to keep track of what's been purchased and whether they like it or not. And the other is a list of recommended books,
Okay.
which is derived from the information there, but it's not the same information.
Yes. Yeah. Okay.
Yeah. The UI doesn't want to know about that. It wants a function which is showing the recommendations.
Okay. Thanks.
Good.
Actually, I have a separate question with you mentioned we can add foreign keys inside here.
Yeah.
Like I say, for example, I have a relation between rating and a user. I would add like I think it'd be something like that. Like I think by default, like it doesn't even add the foreign key at all. Like